Hello friends, this is Mr. Vipul Sonsare. Once again welcome you in our new lecture. Today we are going to see a new topic, that is emulsion. So in the emulsion we will see the particular important point, that is droplet stabilization. So how the droplets of a dispersed phase are stabilized by different mechanisms, that we will see in today's lecture. So this emulsion, so what is emulsion? Is basically a biphasic system where the two immiscible liquids are there. So this, out of these two immiscible liquids, the one liquid is dispersed as a fine globules in the other liquid. So this is basically emulsion, which consists of two different phases. So oil and water in oil type of emulsion, these are the two popular and common types of emulsion. So in oil and water type of emulsion, here you can see, so here the oil globules are dispersed in aqueous dispersion medium that produce the oil in water type of emulsion. So in second, that is water in oil type of emulsion. So here the water globules are dispersed in the oily dispersion medium, that is non-aqueous dispersion medium. So how these droplets of a dispersed phase are stabilized? Because it is thermodynamically unstable system. So during the storage, the instabilities like a cracking and creaming of emulsion takes place. So how the droplets of a dispersed phase are stabilized in the dispersion medium, that we will see in today's lecture. So this is a typical example. So here you can see the oil and water mixture, where these two different phases you can easily understand, and the boundary layer between the two phases, that is the interface, also you can easily observe. But in presence of emulsifier, if you mix the oil and water together, you will get a emulsion. So that also we will see here. So the most important thing, the most important excipients in the emulsion, that is emulsifying agent, which is also known as emulsifiers, which is responsible for a stabilization of oil globules or water globules in the emulsion. So which are the different mechanisms of droplet stabilization that we will see? So first of all, we will see instabilities, how these instabilities in the emulsion is arise. So while the formulation of emulsion, generally we reduce the droplet size of a dispersed phase, and due to this reduction in the droplet size, the surface area of the interfacial contact, the surface area of a dispersed phase droplets increases, and due to the increase in surface area, the interfacial free energy also increases. So for the droplet size reduction, we need to do the work, and this amount of work is equal to the product of interfacial tension and the surface area of the interfacial contact. So as the surface area increases, the interfacial free energy also increases, and this increase in the interfacial free energy basically responsible for the instabilization of the emulsion. So this high interfacial free energy or increased interfacial free energy basically favors the reduction in the interfacial area. So how the interfacial area is basically reduced? So first of all, droplets try to assume in the spherical shape, because the spherical shape have minimum possible surface area. So the droplets of a dispersed phase try to assume the spherical shape. And second important thing, by coalescence of oil droplets. So due to the coalescence of oil droplets, the droplet size is basically increased, and due to the increase in droplet size, the interfacial area reduces. So these are the two important reasons behind the instabilization of emulsion. So how these instabilities we can remove, and how the droplets of a dispersed phase you can stabilize? So the stable emulsion can be formed by lowering the interfacial tension, because the interfacial free energy is directly proportional to the interfacial tension and the surface area. So if you reduce the interfacial tension, you can reduce the interfacial free energy, and thus you can prevent the coalescence of a dispersed phase droplet and ultimately the instabilities in the emulsion. So how you will reduce the interfacial tension? By addition of surfactant. So the surfactant, these are the amphiphilic molecules are capable to fulfill both objectives. They can reduce the interfacial tension as well as they can minimize or they can prevent the coalescence of dispersed phase droplets. So how the surfactant prevent the coalescence of a dispersed phase droplet? By the preferential adsorption of the surfactant on the surface of dispersed phase droplet or dispersed droplets. So in case of oil in water type of emulsion, the surfactant adsorb on the dispersed phase oil droplets, whereas in case of water in oil type of emulsion, the surfactant adsorb on the dispersed phase water droplets. So by adsorption, the surfactant can effectively reduce the interfacial tension, and thus they can effectively minimize or reduce the interfacial free energy, and thus they can improve the stability of emulsion. So three different mechanisms are there, right, of droplet stabilization. So first already we have studied, that is reduction of the interfacial tension. So by reducing the interfacial tension, surfactant can stabilize the dispersed phase droplets. Second mechanism, that is formation of rigid interfacial film around the droplets of a dispersed phase. So surfactant or emulsifier adsorb on the surface of dispersed phase droplets and form the rigid monolayer film around the droplets of dispersed phase, and thus they can prevent the coalescence of the dispersed phase droplets. And third important mechanism, that is by formation of electrical double layer. So by formation of a electrical double layer, that is a barrier for the coalescence of droplets, the emulsifier can effectively stabilize the oil droplets or water droplets which are dispersed in dispersion medium. So just see the first mechanism. So surfactant can effectively adsorb on the surface of a dispersed phase droplet and reduces the interfacial tension. So due to the reduction in the interfacial tension, the surface free energy also effectively lowers, and the reduction in the interfacial free energy can reduce or minimize the coalescence of a dispersed phase droplet and results in a formation of a stable emulsion where the droplets of a dispersed phase are uniformly distributed throughout the dispersion medium. The second mechanism, that is formation of rigid interfacial film around the dispersed phase droplet. So even though the reduction of the interfacial tension lowers the interfacial free energy, already we have studied. The role of emulsifying agent or emulsifier as an interfacial barrier is the most important. So how this emulsifying agent acts as an interfacial barrier. So these emulsifiers forms the rigid monolayer film around the surface of a dispersed phase droplets, and thus they can prevent the coalescence of a dispersed phase droplets and effectively stabilize the droplets. So surfactant, these are the amphiphilic molecules and which consist of two important structural component in their structure, that is polar head and non-polar tail. So on addition of a surfactant in the biphasic system, the water and oil interface, the surfactant adsorb at the interface in such a way that the polar head of a surfactant orient towards the aqueous medium or polar solvent, whereas non-polar tail of a emulsifier or a surfactant dissolve or orient towards the non-polar portion or hydrophobic or oil portion or oil phase of the emulsion. So surfactant are adsorbed at the oil water interface and form the monomolecular or monolayer films around the droplets of dispersed phase. So here you can see in this diagram, so this is a typical example of oil in water type of emulsion. So here you can see the oil globules which are dispersed in aqueous dispersion medium. So on addition of a surfactant form a film around the droplets of dispersed phase, that is oil droplets, in such a way that the polar head of a surfactant orient towards the aqueous dispersion medium and non-polar tail of a surfactant orient and dissolve in oil globules. So in this manner the surfactant form the monomolecular or a monolayer film around the droplets of a dispersed phase, that is oil droplets, and prevent the coalescence and aggregation of oil globules. So this is the simple mechanism of droplet stabilization. So if the concentration of emulsifying agent is high enough, it forms the rigid film between the immiscible phases, that is rigid film at the interface between the two immiscible phases, that is oil and water, and which acts as a mechanical barrier for both adhesion as well as coalescence of dispersed phase droplets in the emulsion. And so because of formation of this rigid film, the surfactant can effectively minimize the coalescence of dispersed phase droplets. Third mechanism of the droplet stabilization, that is formation of electrical double layer. So the repulsive electrical forces between the droplets of a dispersed phase can effectively prevent the coalescence of droplets. So if there is repulsive forces between the dispersed phase droplets, even though droplets come together, they will effectively repel from each other due to the repulsive electrical forces. So these repulsive electrical forces are arises due to the double layer, that is electrical double layer, and the electrically charged groups of the surfactant can be adsorbed on the surface of dispersed phase droplets, and which creates the electrical double layers that we will see. Suppose if you have the oil in water type of emulsion and stabilized by the sodium soap as a stabilizer. So the non-polar tail portion of the sodium soap orient and dissolve in oil globules, that is dispersed phase oil globules, whereas polar ionic head, that is polar head group of the sodium soap orient towards the aqueous dispersion medium. Just see the structure of sodium soap. So the sodium soap is prepared by base hydrolysis of triglycerides. Triglycerides consist of, these are the esters of glycerol and fatty acids. So glycerol contains the hydroxyl group and fatty acid contains the carboxylic acid group. So when they react together, results in a formation of ester, that is your triglycerides. So these esters, if undergoes the basic hydrolysis in presence of sodium hydroxide as a base, results in a formation of glycerol and sodium salt of fatty acid, and the sodium salt of fatty acid is nothing but a sodium soap. So this is a typical example, that is sodium salt of fatty acid, that is lauric acid. So sodium laurate, that is a soap. So next example you can see here, the sodium stearate as a soap, where sodium salt of stearic acid, that is 18 carbon containing fatty acid. So in this structure you can easily observe the non-polar chain, that is your hydrocarbon chain. Long hydrocarbon chain acts as a non-polar tail portion of a surfactant, whereas this ester functional group acts as the polar head of a surfactant. So on addition of such surfactant in oil in water type of emulsion, the polar head of a surfactant, that is hydrophilic head portion of a surfactant, orient towards the aqueous dispersion medium, whereas a non-polar long hydrocarbon chain portion dissolve in dispersed phase oil globules. This results in negative charge to the surface of oil globules because of negative charge on oxygen atom of ester functional group. Now due to the surface negative charge, the positive charge ions, that is cations from the aqueous dispersion medium, basically orient and attract towards the negative charge oil globules. Then negative charge from the dispersion medium again attract towards the positive charge ions, and which results in a formation of electrical double layer. And due to this electrical double layer, the dispersed phase globules are repelled from each other, and thus coalescence or aggregation of these oil globules you can minimize, which results in a formation of a stable emulsion. So, the potential produced by this double layer, that is electrical double layer, creates the repulsive forces between the adjacent oil globules, and thus due to this electric repulsive forces, the coalescence of oil globules can be prevented and results in a formation of stable emulsion. So, these are the three different mechanisms of droplet stabilization in case of emulsion. Thank you.